If anyone's in that position, I just want to remind you guys that I did post scans of the first several homework assignments up in Canvas, so that's not a good enough excuse. You can get those, print those out, do them. What's happening tomorrow? Quiz. What's it going to cover? Chapter 1, 2, and 2, 3. Good. Because I skipped 2-1, I came back to it yesterday. Yesterday we got up, we skipped 2-4 for the moment. We're going to come back to that today. We did section 2-5. And what was that all about? What did we learn about? What was the new stuff we learned about yesterday? Does anyone remember? You guys were here, right? That wasn't me hallucinating. What? I never know. What is it? Limits. Okay, getting limits from graphs. And also graphing them, that problem was exciting. When I gave you what the answer is supposed to be, and you had to create the problem, make the graph that actually had limits. Okay, what else did we get from that? That was something we did first. Yes?
We found the slope of a specific point on the graph.
Cool. Found the slope. Secant lines. We talked about secant lines. What about removable chunks? Okay. Alright, okay. The quiz tomorrow is not going to have continuity stuff on it. That's section 2.5. So it's just going to be chapter 1, 2, 2, 2, 3. So it should give enough people to get most of the homework done by Thursday. Right now, I would say you should be in like section 2, 3 would be better to be on track. Are you guys with me? And then you go back and do 2-1. Okay. So if there are no questions, we'll just get right back into where we left off. First thing I want to say, I just found out something that made me very sad. I reached out to the success coach office and I asked them about getting somebody to come out to present, and they're like, oh, we don't have anybody this summer because we lost all of our success coaches from last semester. They all graduated. So they have a brand new slew of them that they're training right now. But she did say if you went to the success coach office, the person who's in there could help. They know they're one of the people that are training the other people. You guys with me? So you can still go to the success coach office if you have issues and you're not sure if Grossmont has an answer to those issues. You guys kind of with me? Like, you don't have a car, your car's gone, you're doing the bus and the bus is too expensive, then they can tell you how to get in touch with somebody that would reduce the cost of bus fare, for example, right? Okay. Hey. So, that's number 1. No general success coaches over this summer, but you can still go to the office and get help. Okay. I want to formalize a couple of things from what we've been doing. So for example, there's in section 2.3, I think it is, they talk about limit laws. And these limit laws are kind of silly. We've actually already used them. So I'm going to kind of formalize them a little bit. First thing. So for example, sorry.
This is
2.3. Let me make sure. Yes, 2.3. Here's an example. What would you guys think that this limit is? Bless you. What is that limit? Don't overthink it. What's that limit? What do you always try first? Yeah. Sure. What do you get? -3. Is that cool? We just used the limit law, and the limit law we used is if I have the limit as x goes to 1. As x goes to a of f of x plus or minus g of x, that's equal to the limit of each piece added or subtracted. All right, that's kind of silly. Yes? It looks like the limit distributes. Dear God, that's not what's happening. Because that doesn't say limit times shit. That says limit of stuff. It just happens to be a process that looks like it distributes. There's a lot of things in mathematics that looks like they distribute. How are we doing so far? We've already applied this silly notion. You got the notion. Okay. And not surprisingly, it works for multiplication. Limit as x goes to a of f times g equals the limit as x goes to a of f times the limit as x goes to a of g. Okay, right? Basically, most of the limit laws say if you have a function that's composed of other functions, you can just take the limit of each piece and then put it all back together. Okay, I like it. Is there anything else exciting with this stuff? Not really. Blah, 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 blah. No, okay. One little thing I will say that leads into something else is if I have the limit as x goes to a of, what you got, Jeff? It doesn't matter. The cube root of g of x, that is the cube root of the limit. You guys with me? So when you get to the homework and it says evaluate specifying the limit laws you use, you just have to go back in the section and just look at the limit laws. And if you have a subtraction, you tell it limit law number, whatever. You guys with me? Okay. They're almost too simple to really sit and list and make a big deal out of. But we do need to take a moment. Every time we define a process in mathematics, we do need to talk about how that process works when there's multiple things it's acting on. Not every process is distributable like this. Okay. Blah, blah, blah. Oh, something this leads into, let me see, where's this guy? Blah, 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 blah. No. Yeah, here it is. Is it this one? No. This kind of leads into the idea of this. If I have a function inside of another function, I can just take the limit inside, but that only works in specific situation. It only works if if f is continuous at x equals b and g of a is b. Oof. So it needs to be a continuous function for me to be able to take the limit inside. Up here, is the cube root continuous? Does anyone know? Yeah, if you know what the cube root function looks like, does anyone know what the cube root function looks like if you graph it? Not cube root. Yeah. Yeah. So it looks like this. Yes? You with me? And real quick, why does a parabola, when it falls over and becomes an inverse, why does the bottom half fall out? Poor little dude. Sounds like a TNT moment. So the parabola leans over, becomes a square root, and the bottom half falls out.
Can't take the square root.
Can't see with negatives. But cubes are cool with negatives. So their cube root just flips the cube around and makes it become this. Are you guys with me? Finding the inverse is just switching the x's and y's. Do you guys remember doing that?
Yeah.
You flip it over the y equals x line. And I sometimes tell my students they remind me of the Nazca lines in Peru when you make the pictures. If you don't know what that is, look it up. Okay. Blah, 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 blah. If I want to check to see if a function is continuous on some interval, if I want to check to see, take the if away. F of x is continuous in some interval a, b, if f of x is continuous at each x in a to b. can somebody read mine? Are you guys kind of with me? We know how to check continuity at a point. How do I check continuity at a point? How do I check to see if a function is continuous at a point? So let me give you some stuff to work with. We're given this function, and I want to know, is this continuous at x equals c? What would I need to check to see if it is continuous? You could do it, you could do it. We did this, we had all these statements, and then we decided one statement is all I needed. It combines the two ideas we've been looking at, limits and function values. What does it take for it to be continuous? If I have a graph that's doing like this, here's C, and it does this, could it be continuous? No, right? A little fusion dance, you're gonna get the fat little emoji, it's not gonna work. Huh? It has to connect. We have my triangle. So, what does that mean? What am I doing here? What is this? The limit, okay. And the limit has to equal what? No? So not only does it need to look like they're approaching a certain value, the same value, yes? But the function actually has to be that value, yes. So to capture that, are you guys with me? Not only does the road have to agree on both sides where it's going, it has to actually get there. One of that is limits, agree on where it's going. The other one is function output, get there. So if I marry those two things together, I get continuity. If the limit as x goes to c of f of x is equal to f of c. So that says f of c has to be defined, the limit has to exist, and those two agree. That would be continuous. The road is going to the same place from both directions, and it actually gets there. There's no giant hole that's going to swallow that car. And then I wonder, why did I move to Florida? I did my time in Florida. Don't go there, kids. How are we doing so far? That was a big thing we talked about yesterday. If I have an interval of inputs, and at every point this is true, then f is continuous on that interval. Question. So let me show you a very specific example. I love you guys. Can you guys take a moment? Can everybody just sketch a decent little sketch of a square root function? Sketch a little sketch of me. Sketch a little. Give me a quick, rough, decent scale point sketch of square root of x. Go. That would help. Huh. So what's the first point you would plot? 0, 0, that makes sense. And then I can plot 1, 1, and then I could plot 4, 2. I'm gonna be nice to myself, because I'm the fool trying to plot this. I'm not gonna do the square root of 2 and try to plot that. So then you get, yeah! Okay, now, would you say that this function is continuous on its domain? Yes. What about 0 though? Like why is it continuous here? Why is it continuous here?
Because both sides mean the same.
Both sides limits agree, and the function's output is equal to the limit. So what about 0, 0? Where do things kind of fall apart there?
There's no other side, it only agrees with
Yeah, there's no side. It goes, yeah, and then void. According to the square root function, the whole other part is just void. It's the nothing from Neverending Story, yes? Okay. But here's the trick. I am going to tell you this is continuous on 0 to infinity. Did I include 0 in my statement? Yes. So here's the idea. It is unfair to require endpoints to have limits from both directions because they inherently don't have the other direction. So the way we do endpoints specifically is I just need a one-sided limit. So to be continuous at 0, I just need the limit as x goes to 0 from the right to equal this. And does it? Does it? The limit looks to be 0 and the function value is 0. Are you guys coming with me? I don't want to make a huge point out of this, but I can't remember. I think there's one or two more problems where this becomes a little more important. Endpoints, we make it a little bit more relaxed for them because they have an entire half of the universe that doesn't exist. Yes? Which one? Well, I haven't given one out yet. Sorry. Okay. How are we doing so far? Is that all right? That kind of makes sense, yes? Poor little dude. How could it be from that side when that side doesn't exist? It's a little much. Okay. All right. Blah, blah, blah. Here's something kind of silly. If f and g are continuous, yes? F and g are continuous on some interval. What do you think is true about f plus g? If f and g are both continuous on the interval a to b, what do you think is true about the function f plus g? If f is defined as continuous at every point, every input between a and b, and so is g. When I do f plus g, do I get a continuous thing throughout that interval? Is it? Are you guys at all with me? I love you guys so much. F is continuous on a to b. What does that mean? At every point in between a and b, the limit equals the function value. Yes? So what do you guys think is going to be true if I just add the two functions together?
They're continuous at the same end.
Yeah, is there any way to just add two functions together and make there be a problem point? No. You guys understand? If f of 2 is 3 and g of 2 is 5, f plus g of 2 is 8. I just add the two out and I get this nice continuous. Okay. So this kind of hopefully makes intuitive sense. If I have two functions that are each continuous on some interval, when I add them, I get this new function that is also continuous. And if I subtract them, yes? What about if I multiply them? Also continuous, blah, 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 blah. What about if I divide them? Where's this going to have an issue? Now I've done something that could introduce an issue. Where's the one place this might be discontinuous? If
0.
Or saying,
so be more specific. If what is what?
the opposite minus.
If the output of what? You can do it. What makes something discontinuous? What's one way if the bottom is
0.
what's on the bottom? So if there's an input that makes G, there it is. So if would only be discontinuous at a point C in A to B. Good Lord, Jeff, if you could write, everybody would be so happy. Leave me alone. Let me stop for a second. Have you guys seen this before? All this means is element of. C is an element of AB. So it just means whatever the interval AB is, I've picked out one of the points in there. Yes? If A to B is 5 to 7, 6 could be C. 5.3 could be C. Any number that's in there. So all that little weird looking E dude, it just means is an element of. Okay.
Every day that's in between the two.
So this would only be discontinuous at a point C where G of C is
0.
0. There. Otherwise, it's continuous on A to B. So there's this idea of functions inheriting the properties of the functions that went into creating them. Yes? This is the one that, since I'm divided by g is 0, it also freaks things out. Blah, 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 blah. Okay, get it. Okay, that's fine. Let's see, what else do I want to talk about? This one. This is really big. Here is a beautiful theorem. Page 120. This theorem I'm going to come back to a few times this semester. And by the way, next semester too, like if you take 280. Or it will be known as C2220 next semester, because that just makes more sense. Read through this theorem. This theorem kicks so much ass. Okay. We just saw an example with root function, square root. Obviously, the square root function is continuous on its domain. It's not continuous at -1, because it doesn't have to be. That's not even a valid input. So that's why this one says, these functions are continuous at every number in their domains. Rational function. Can somebody give me an example of a rational function? Yeah, kick ass. Where is this discontinuous? Oh shit. Unfreeze. Where is this discontinuous? Yes. But what's true about 0? What's the domain of this guy? What's this guy's domain? Infinity at 0, skip 0, go to infinity. So, listen. It being discontinuous here is actually a very silly thing to say in the first place. It is continuous everywhere on its domain, because the only number it would be discontinuous at is not even in its domain. You guys follow? So real quick, we're going to come back to this later. I don't blame you for not saying this earlier, but what about this guy? Where is this guy continuous? Don't say on its domain, Jeff. No, be more specific. Where is it discontinuous, and then is it continuous on its domain? How would you figure out where this thing is discontinuous?
Figure out whatever the bottom value. Whatever you plug in the bottom value
Yeah.
is 0.
And the way it's written right now, the bottom sucks. It's not telling us anything. How do I put it in a chair, turn the spotlight on, and make it tell us some shit?
It can't be at 4 and 3.
Why? How'd you know that?
I factored
There you did. So if I back into that boy, then that becomes nice. This becomes x minus 4, x minus 3. So what is this guy's domain?
negative infinity to 4.
Infinity to 3. 3 to 4. 4 to infinity. Is it cool everywhere else? Yeah, it's continuous everywhere else. What is happening at 4 and 3 graphically? What are they the locations of? Asymptotes. What kind of asymptotes? Vertical. Cool. Right? That's the Star Wars, the shield generator still operational. Pull up. Ah! It's a trap. Okay. Or you don't have to think about it that way. That's just too deep for you. That's fine. Are you guys still with me? So there's going to be quite a bit of overlap. And you're not going to believe this. But the class we call pre-calculus, it's going to show up a lot here. So you guys have already discussed asymptotes and pre-calc, horizontal asymptotes, vertical asymptotes. Those have direct connections to limits, which is why very often a teacher will show limit notation when they're teaching those things. Okay. Oh yeah, that's right. So one more thing, and then we'll get into something more specific. There is our first major theorem. Has a kind of a possibly daunting name. Intermediate value theorem. This theorem is actually really silly. And from now on, it's going to be known as the IVT. Just as the less I have to write, the better it is for everybody. This theorem is really dumb, but I love it so much. I want you to understand, we need this theorem in order to do more advanced stuff. So I need to explicitly state this theorem, but once I get it all out, you're gonna be like, duh. Well, let's see if you agree, I don't know. Let's say I'm given a function that's continuous on A to B. So let's say it's like, it looks like this. Hi. No, Jeff. It's got to be a function, Jeff. That's all right. I'll pretend like that's fine. Yeah, that's fine. That works. Yeah. Okay. Y'all agree that function is continuous on A to B?
Yeah.
Give me a little license in the middle. I should pass vertical license. All intermediate value theorem states. Okay, actually, let me see what you guys think about it. What's the domain of what I've drawn here? A to B. Oh, man. What's the range of what I've drawn here? So what is it explicitly? It's f of x, yes? So what output is this? And what output is this? So what's the range? F of A to F of B. So, all this theorem says is any number between F of A and F of B. Let's say like n. Anything in between, then this has to go through it. There's no way to escape. I need you to understand this. Are you guys with me? I don't care what you pick between those outputs. It must go through every point in the middle at least once. Yes? If I made a graph like this, it would go through it many times. Are you guys at all with me? Do you guys understand it? It's remarkably stupid. Yes? I need you to really get this. And I'm not trying to make you feel bad if you don't know what I just said. If I take any number between f of A and f of B, any number between them, that function has to have that output at least once. Because what's the only way I could escape doing that? So let me give us a clean graph here. What if I know, here I'll do it over here. What if I know I start here and I go here, and I know it's continuous? Can you escape having that output? The only way you could escape having that output is if you were allowed to jump. But what would be true then? It would be discontinuous, and what did we say at the very beginning of the intermediate value theorem? The function given is continuous. So that's the part that makes it dumb. Since it's continuous, yeah, you're going to hit every damn output between the two because you have to be able to connect the 2 points. I could only escape that if I was allowed to jump or have an open circle somewhere. Yes.
So essentially, intermediate value theorem is if the range was 1 and 2, and you pick 1.5 has to show up at least one time between it.
Has to have that output at least
You can't
once.
do 3 because it goes out.
So like this could look like this. Yes? So how often did I hit n? It looks like maybe once, twice. So here's the trick. Can you guys tell me what's true about f of A? Give me one thing that's true about f of A. It's a very strange question. I don't care.
What's the range?
It's positive. Kick ass. And it is in the range kind of, arbitrarily. And what's f of B?
Negative.
So if I have a continuous function where one output is positive and one output is negative, or vice versa, what must it have between those two?
Like 0.
It has to have a 0. It has to have an x-intercept. So do you see how this little dumb little thing where if you try to draw a line, can you get away from it? No, of course you can't. You have to draw through every point. But then it immediately leads to, if I know f of 3 is 7 and f of 4 is -1, what's true, there's got to be an x-intercept between 3 and 4. That's actually pretty powerful, right there. I can just plug shit in and figure out if there looks to be an x-intercept somewhere. Okay, how you guys doing? At least one intercept, because how many intercepts does this actually have? 3. There's 3 x-intercepts, yes? So as long as one is positive and one is negative, it's got to go through 0 at least once. It's got to, because it has to go through every possible output between.
So you could have a minimum of one, but it could also have more than one.
It could have infinite, to be honest. Because you could have a cosine function that's just kind of going crazy. Or you could have, here's a really dumb thing. You ready? Beep, beep. Here it is. Here's A, here's B, and here's the function. There's the function. That's a dumb. Are you guys with me? What is the definition of f of x in this case? You could do it.
Zero.
0. Is it continuous?
Yeah.
All day. Therefore, and this one's kind of dumb. You guys see how this is really dumb? It's kind of like the range is 0. So there must be at least one place where it gets 0. And in fact, how many places does it have a 0 output? Infinitely many. Okay, that's kind of a silly way to do it. Let me stop for a minute. Love you guys. Now listen, I want to address something real quick. I get this sense, is this true for anybody? Have you ever been sitting there in all of the 2 and whatever portion of a day we've done this and thought to yourself, what does this mean for me? What am I going to see? What am I going to see in my homework? So you're going to have that moment, I'm really sorry, because I need to explain the idea, and then I always bring it back to the nuts and bolts, yes? The more you can connect to the idea, the less you're going to memorize shit, the more you're just going to do what makes sense. And do we all have infinite space here? Do we have infinite space? If you do, what? We don't. We only have so much space up here, yes? So if you're trying to go pretty far in STEM, you have got to start to realize all the math I can do, I do not have memorized. Holy shit. I've just found there are certain things you memorize, and then on top of that are just things that make sense. Because I understand the concept, yes? Okay. So what you're going to see in the homework related to this, I love some of the problems related to this are awesome. So just get in there and try them. I'm not sure how you feel when I say that. Probably bad. I'm sorry. If I say I love something, normally students are like, oh shit. But you got to get in there and try them. Yes? Okay. All right. Is that okay for intermediate value theorem? Like, for example, if I gave you this function here, oh boy, Jeff, what have you done to yourself? What is f of 0? Negative 1. It's crazy. And what is f of, what's f of 1? 1. What must be true then?
It's continuous through.
Well, okay, I appreciate that. The function given is a polynomial, therefore, according to that crazy-ass theorem, every polynomial is continuous on its domain, and every polynomial's domain is all real numbers. So this function is continuous, period. That's why I didn't even give an interval, like I said there. Because every polynomial is continuous everywhere, period. So it's continuous, in which case, what's true, given those outputs we just got? What must be true?
But it also holds true for that intermediate value.
Between 0 and 1, there must be
X-intercepts.
at least one x-intercept. And what is it? At 0, isn't it below the x-axis? Yes? At 0, it's at negative 1, yes? At 1, it's at 1, yes? It's continuous, so there's got to be at least one place that goes through the x-axis. You guys with me? Isn't that kind of nice? Wasn't a whole big part of pre-calculus finding roots? Did you guys ever study Descartes' rule of science? Yeah, some of you guys look at me like, you made us do that shit, right? You suck. And bounds and synthetic division. You guys remember this stuff? Some of you guys are looking at me like with blank faces. It's not good. I will review synthetic division because it's stupid awesome. Synthetic division kicks a lot of ass. But do you see what I just did? Now I know there's an intercept between 0 and 1. I kind of like narrowed down my search parameters. Yes? So if I had a list of all the possible roots and one of them was 1/2, I'm like, let me check that dude out. Because I just saw there's a 0 between 0 and 1. Okay. I'm not saying this has any nice answers because I just made it up out of nowhere, but that would be something else you could do. Okay. Yeah. So, what I want to focus on today, those are all little bits and pieces that showed up in the chapters we've done. I just wanted to formalize those. I want to, first off, I want to bring us back to a problem we did before. I don't know if you guys remember this. I'm pretty sure we looked at this. This was on the
sheet.
yeah, one of the sheets we did. Yeah, there it is. This was on this sheet here. Come back to me. Right? And we factored this thing. And we got the x minus 3's to go out, and then I put the x equals 3 in there. And when I put 3 in there, I get 24. Okay. We did that. So coming back to the picture here, I've got my function. What kind of function would you say this is? Is it really obvious when you see this? No, not necessarily. Although if you think about it, it's a squared x divided by a single x, so your answer should be a single x, which means linear when it's x to the first power. But still, it's not like obvious. Yes? So that function is this line everywhere except that one point. That one point freaks it out. So, what's the limit as x goes to 3 of that function? 24. Does it matter that f of 3? Well, actually, what is f of 3 for this function? Undefined. Yeah. You guys still with me? Okay. What I'm getting into right now is the other side of that sheet we did the other day. I'm going to talk about a definition of close. Because we've used the word close a few times already. And it's not an immediately obvious term. I think I told you guys, is 1 close to 2? In everyday occurrences, yes, 1 is close to 2. If I was a little kid going to an ice cream thing and I had $1.02 and I wanted to buy the thing that I always get for $1, and the guy said it's actually $2, is 1 very far from 2? Yes, for me that's true. Yes. So in mathematics, it still depends on the context. But if you ask any mathematician, independent of context, would you say 1 and 2 are close? They're almost always going to say, no, they're not close. They're not close. They're really not close at all. So, the idea of close in mathematics, we need to develop a more formal way to look at it. And along the way, well, primarily, we're going to look at a more formal way of what a limit means. So you all agree the limit is 24, yes? What does that really mean for the limit to be 24? Like, if I plug a 2 in, I'm at 20. Is that close to 24? Not really, right? So when am I supposed to start seeing something related to 24? I'm not sure how to say this. You guys with me? If I plug a 0 in, it looks like I'm at 11 or 12. I don't know. Yeah, it looks like 12. You guys see what I'm saying? That's not 24. What are you talking about? When should I start seeing something related to 24 start happening?
2.9 right now.
Okay, good. So if you broaden what you just said, when your inputs get close to 3. And there's that damn word again. Yes? The closer I get to 3, the closer my output should get to 24. If that doesn't happen, then 24 can't be the limit. So, I want to really formalize this. So here's what I'm going to do. Let's do this. Would everybody agree that 2.9 for everyday use is pretty close to 3? For most people, that would be pretty close to 3. If you said it cost $2.90 and then you're like, actually it's $3 now, I'm like, all right. What about 3.1? Yes? Okay. Do you see how I've got outputs related to those inputs? Yes? In fact, let's see what this is exactly. This output is 24.4. Stay with me now. And this output here is, you can do it, 23.6. All right, so let's see what's going on here. Yeah, not too bad. Okay. Let me zoom in even closer, I think, because I like this. We could do this. Yeah, good. All right, so here's the idea. If somebody came along and said, I've kind of done this backwards, but we'll be all right. I want you to be this close to 24. I want to be this close to 24. Then I would say, okay, I have to be this close to 3. I have to be this close to 3 to be this close to 24. So the idea of close then, it really means if somebody comes along, let's do this the other way. Let me turn these guys off for a second. All right, so 24, right? So let's get like 24.01 and 23.99. Do y'all agree with me that's damn close to 24? Are you guys understanding? In fact, why can't I even see the separation because it's such a small... What have I done to myself? Oh yeah. What have I done to myself? What did I do?
23.99.
23.99?
No, you put 23.99. Move it this way.
Oh, thank you. Good Lord, Jeff. All right. There it is. Okay. For a moment, I was like, why is the other thing not showing up? Okay. I have created kind of like, if the limit really is 24, some random person could come over to me, right? Not like this is going to ever happen. Some random person could come over to me, oh yeah, if it's 24, then I want you to be within 0.01 of 24. Do you see how we just set that up? Can we find inputs that would always let me be that close? Do you see how to do it visually? How do I do it visually? Well, right there, do you see that? As long as my input is more than 2.9975, now we're going to get to the other side too, right? But as long as it's close to 2.99 but above it, I need you to be really with me. If I put this input right here, this input, am I in there? Yes. So if I'm in there, that means I am close as this random person wanted me to be. And then on the other side, so help me out. Somebody write that down. I'll write it down. 9975. Okay. And on the other side, 3.0025. Okay. Yeah, I forgot. We have a linear function. It's going to be easy to. So as long as if my inputs are 0.0025 away from 3, my outputs will be within 0.01 away from 24. Let me say this again. This is huge. Some random person came up to me and said, oh yeah, well if it's 24, I want you to always be within 0.01. And I'm like, all right, all I gotta do is let my inputs always be within 0.0025. So somebody said, oh, well, okay, it'll be in 0.001. Then all I have to do is like shrink this dude, yes? I want everybody really with me. If they said, no, it's too easy, I want you to be, this is going to be a little bit freakier. Oh boy. I want you to be that close. Is it a much harder thing to do now? Now I've got to be that close to 24. Can I do it? Yes, now as long as I'm 2.99975 and 3.00025. Yes, I need you with me. This is really stupid. If the limit really is a number, then that means at some point I have to forever be arbitrarily close to it. So that arbitrarily is this guy. Oh yeah? Be within this, be within this, be within this. And if I could do that, no matter what number they give me, that is the limit. So if we thought the limit was 24.0007, then it would look good so far. But could the guy give me a range where I would suddenly not be in there anymore, if that's what I thought? Yes. So if the number that I think is the limit, if I can always get as arbitrarily close to it as somebody wants me to, it is the limit. Okay. This is the concept. We still have to develop what this looks like on paper. There are a few problems in the homework that are they give you this picture, and they ask you to figure out how far you gotta be on the x-axis. So let me formalize a couple of things. By the way, this is I'm not going to say that. This is the first section. It's kind of funny, we were talking about proofs earlier. This is like our first little baby step into proofs, which is so exciting. And normally people kind of have a visceral reaction to that. But it's a little baby step. We're going to be okay. So when I talk about let's see, what do I put here? I'll just put this, yeah. When I talk about being arbitrarily close, let's say the limit as x goes to, let me make this a, is L. Okay, so let's say this is my claim. The limit as x goes to a is L. That means somebody should be able to come along and give me a value to be within. What that is, the symbol we give it, now this is going to be exceptionally exciting for you guys because I used this in a different way earlier. This is going to be epsilon. It's a little Greek letter epsilon. It's also used for is an element of, which is very exciting. Epsilon controls the idea of close for my outputs. So I need to be so close to my outputs, and then I need to figure out how close do I need to be to my inputs. Now, very quickly, did you guys notice when I changed the epsilon earlier from 0.01 to 0.001, did our delta, I didn't talk about that, did our distance on the x-axis change? Did I have to get closer to my inputs to stay within? Yes, I did, right? Yes, I did. So there is a relationship between these two things. On the x-axis, this distance is called delta. No relation to the airline. Okay, nothing too major. You guys have seen Greek letters before. Math people, we love them. They make them look, more formal. Sort of like the Super Bowl using Roman numerals. Okay. So here's how this works. Some random dude, or dudette, I don't know, comes up to me and says, so our claim is the limit as x goes to a of f of x is L. Yes, that's our claim. And they say, oh, okay. Well, then I want you to be at most, or let me see, less than epsilon away from L. That's this here, yes? That was the lines we drew going this way on the graph. I want you to be less than epsilon away from L. And we have to figure out, we must determine delta so that that's true. Okay. So epsilon gives us the idea of close on the y-axis. Delta gives us the idea of close on the x-axis. Very often we'll kind of say on the side, epsilon is greater than 0, delta greater than 0. And they're normally considered to be very small, which kind of makes sense. Barely more than 0. Okay. Is everybody semi with me so far? The concrete example we did earlier, when this shrunk in size, this also shrunk in size. So do you guys see how there must be a relationship between epsilon and delta? That's what we're going to try to figure out, is if somebody gives me an epsilon, what do I have to make delta to be sure I'm always that close? Okay. So I'm going to formalize these two statements. So the statement, I want to be less than epsilon away from L, I formalize like this. What function in mathematics deals with distance? And that's why it's always a positive output. Do you guys know? Absolute value. Absolute value deals with distance, which is why it's always positive. How far is -4 away from 0? It's not -4 away, because then it would be like, you're not -4 feet away from me if I turn around. Because then it would be in there. Okay. So the way to say this formally is I want the difference between the function and the limit to be less than epsilon. This says the distance between the outputs of the function and the limit are less than epsilon. That's exactly what that thing was we did on the graph earlier. We set up this range, the distance between the function output and the limit, I want it to be less than epsilon. I'm setting up that little cage to catch that in. Yes? And I want that to be true if my inputs are delta away from A. Okay, I like it. So this is the formalization of what we're talking about. Those two, the first one were these lines, and the second one is these lines. Yes? Look at this little box I don't want to live in. I love you guys. So here, let's do this. So the way this normally works, the whole proof, given epsilon greater than 0, some random dude comes over and says, I want you to be within 0.01. So given epsilon greater than 0, by some random dude, we need to find delta greater than 0 so that when x minus a is less than delta. All right, so let me say in English what we got so far. Some random dude gives me a distance. We then need to respond by finding a distance on our x-axis that will keep me that close in my outputs. Because we all know, you all inherently know, the idea of limits are all about getting close. We've used that word continuously, no pun intended, about limits from the beginning. Yes? So they come along, give me the epsilon. We need to find a delta in response so that when we are that close to our input, then our function values are this close to the limit. If that's always true, no matter what epsilon is, the limit is true. You all look as excited as expected. Here's the nice thing about this. These proofs, with the functions we're able to work with so far, end up being remarkably straightforward. I think I signed like one or two that was meant to push you a little bit, so we'll see. In the section 2.4. Do you want to try a concrete example? If I were you, I'd be like, good Lord, Jeff, yes. Can we do concrete now? All right, so let's do the one we just did. Given, what was it, 4x minus 36, x minus 3? Yes.
It was 4x squared.
Oh, squared, yeah, thank you. Okay. Prove the limit as x goes to 3 of f of x is 24. That's the question, right? Given that function, prove that the limit is 24. Now, when I use that specific language, when I say prove this, and I'm going to be very explicit on a quiz or a test, I'm going to be very explicit when you have to show me the proof. Because normally, if I were you, I'd just factor the damn thing and be done with, yes? And I don't blame you right now for sitting there going, why would I just do that shit, Jeff? And again, it's because the idea that this sets up, we're going to use it several times this semester for increasingly more difficult kind of things. So this is just like baby's first step. Okay. So here's how the proof works. Given epsilon greater than 0, we need to find delta greater than 0 so that when x minus, what is it, 3? Yes. Is less than delta, then 4x squared minus 36 over x minus 3 minus 24 is less than epsilon. Let me just let you absorb that. I just put specific things in place of what I had written earlier, right? F of x minus L. Yes? And I just put f of x in, and I put L in. X minus A. X minus A, the input is 3 that I'm curious about, yes? So if I am this close to 3, I must be arbitrarily close to 24 in my outputs. Okay? Because I understand. Those sentences are really easy, but then when I start writing the math of it, it gets a little bit lost. And that's why I want you to realize most math things you can read like a sentence. That's the sentence we said about being close in the x-axis. That's the sentence about being close in the y-axis. How you guys doing so far? You guys all right? You guys look mildly upset stomachs. That's okay. That's a normal reaction. Okay. Here's where students kind of understandably don't get this. We're going to do something called a construction proof, and I'm just going to construct delta. I'm going to construct what delta has to be. And this is going to feel like cheating, but it's condoned cheating. It's not really cheating. We're doing a construction proof, yes?
No, I don't have a question.
Okay. So here's how this works. I'm going to do some side work over here. This is where we want to end up, yes? I want to end up here, yes? Yes? That's where I want to end up. So this, I don't blame you for feeling like this is cheating a little bit, but again, this is construction proofs work like this. The minute I make the function any more difficult, the level of difficulty of the proof goes crazy. So on one level, once you see this, you're going to know the answers to everything right already. You just have to write the formula. Okay. I'm going to start with where I want to be at the end, and then I'm going to simplify. How do I simplify what I've written? What's the most immediate thing you do to simplify it? Factor. Can we just get to the cut to the chase? Won't this be this? Is that cool? We've done that before, yes? Factor it, get x plus 3, x minus 3. The x minus 3's cancel, so you get 4 times x plus 3. Is that cool? Okay, I'm going to pretend like that's cool. Then if I distribute, I get 4x plus 12 minus 24.
So for absolute value of 4x minus 12.
Sorry?
So it'll be absolute value.
Yes, sorry. So the absolute value of 4x minus 12, yes? I love you guys. I love you guys. You're doing great. This section is definitely not intuitive. It isn't. It's a departure from what we're doing in a way. It's more solidifying very formally the limit stuff we've been doing. Did we need this to be able to do the limit stuff we did? No. Could I have skipped this entire section? Yes. And that's where you all kind of go, do that then. Do that. I always hate when I skip this section because later this semester I could say just something really quickly and it would have made so much sense. All right. One last thing I could do. If I factor a 4 out, I'm just going to do that. I could divide by 4. Is that cool? Do you guys see that? I'm allowed to do that because 4 is positive. If I factor a 4 out, the absolute value of 4 is 4, and then I divide by 4. Does that look at all familiar to anything? Did I uncover something? Do you guys see what I just uncovered? Does any part of that look like something somewhere else in this problem? Yeah. What did I need this to be? Less than delta, yes? Can you tell me what delta has to be? Epsilon over 4, yes? So did we just construct what's got to be true about delta in order for the proof to work? Do you guys, I need you to see this. X minus 3 must be less than delta. Did we just figure out a value that x minus 3 must be less than? Yes. So then what do I want to set delta equal to? Epsilon over 4. Yes. This feels like cheating. If it doesn't feel like cheating, you're not quite seeing it. It should feel a little bit like cheating. So we're not done though. That's just the beginning. But we're almost done. Don't freak out. Let delta equal epsilon over 4. I'm going to make this concrete in a minute. But for right now, we got to live in the world of proofs. Okay, this is where things get really nifty. If I let delta equal epsilon over 4, when x minus 3 is less than epsilon over 4, now here's the funny part. Because given epsilon greater than 0, we need to find delta greater than 0. Did we? Yes, we found it. So that when this is true, then this is true. So we found a value for delta. And now we got to show when this is true, when this is true. And you're not ready for this. I just do all the shit we just did. I just do it backwards. Multiply by 4. Make this plus 12 minus 24. How did I know to do that? Because it's over here. The proof says, when this, then this. So I must start with the x statement and then end up with this statement. And then I just keep going. This will be 4x plus 3 minus 24 less than epsilon. This will become 4x squared minus 36 over x minus 3 minus 24 less than epsilon. I'm just doing everything backwards because I could factor this. I could multiply top and bottom of this by x minus 3 and make it become this.
On the test or quiz, we don't need to actually go because you'll be able to know that we went if we just put the original formula back in. Is that like working backwards and putting everything backwards all over again?
You ready? Are you guys ready? To get full credit for this, you have to show me all this.
Oh, yeah?
Okay. If you don't want full credit, you don't have to show me everything. And did we show it? Did we just show that when this is true, then this is true? I mean, yes, obviously, yes. If I make this less than epsilon over 4, is it true that my function values are epsilon away from 24? Yes. My function outputs are less than epsilon away from 24 if I make my inputs less than epsilon over 4 away from 3. Now, I promised you I would make this concrete. By the way, do you guys notice how silly this proof really is? I mean, once you do the side work, you're basically done. You just have to copy it backwards. And don't just say, well, let's put it back. No, write it down, because I'm an asshole. Just get used to that. But coming back to this, I want to make this really concrete. What did we just say delta has to be? If somebody gives me epsilon, what did we just say delta had to be? Epsilon over 4. So let me make this a little bit better to see. Actually, screw it. Can somebody tell me, in this example I've given you, what is epsilon? This is perfect. Can anyone tell me what epsilon is with what I've got up there? What is epsilon again? Where is it on the picture?
The what?
Y-axis. It's how far these get away from what? The limit. And what's the limit in this problem? 24. Not the input, but the limit, 24. Can anyone see what epsilon is?
Plus or minus 0.001.
0.001. You guys with me? Do you guys see how epsilon is 0.001? Because epsilon is how far away I am from the limit on the y-axis. What would delta have to be then? We already figured it out. Whatever the epsilon is, what did we just figure out delta has to be? Take epsilon and what did we just figure out? What did we just get for delta?
Divided by 4.
Divided by 4. Can you guys, what is 0.001 divided by 4?
0.00025.
Okay, hold on to that. You guys with me? 1/4 is 0.25, yes? So it makes sense. 0.001 is 0.00025, yes? You guys with me? Stay with me now. So if I am 0.001 away on the y-axis, we just predicted that we have to be 0.00025 away on the x-axis. How far away am I on the x-axis? Well, what's this here? What point is that?
0.000.
How far away is that from 3? 0.0002 freaking 5. Yes? That's the connection.
The rainbow.
And if I go on the other side, yes? So that's the concrete shit we just did. We just said, whatever they give me epsilon to be, as long as I make delta 1/4 of that, I'm good. And what epsilon does that work for? Are there any epsilons that doesn't work for? No, it works for every damn epsilon. So no matter how close they want me to get, I can get that close. That should be what a limit means. What's a limit mean? I get really close to this number, okay, then you better get frickin' as close as I want you to get. That's all this says. Epsilon is just some guy going, well, yeah, once you get this close then, you know, and we're like, okay. Yes.
Is it always 4 or over 4 or is it?
Hell no. Some of you guys might realize this is why this is over 4. What was the slope of the line that we ended up with when we simplified was 4? So that's what I mean. You start to realize you should know the answer at the beginning, and that's why I didn't assign that many problems out of this section, I don't think. How many problems did I assign out of 2, 4? Past Jeff is an asshole, even more than me, so you never know. Okay. Past Jeff, I don't know who hurt that guy. Okay. So just to point out, and to make you guys do something, because I'm tired. Does everybody have this handout that we worked on yesterday? Does anybody need, give me a second. Oh, okay. This handout here. Oh, okay, wait a minute. Let me grab more. Do I have more? How do I not have more? Oh, I can use, wait, which one do I want? Oh, the continuity one. This, here we go. All right, sorry, who else? Everybody else good? Everybody else good? Oh, you. So let me do two things. So here's the kind of like me trying to show you on the paper what's happening. Here's kind of like the formal write-up. Yes? Here's an example. This is basically what we just did. I forgot that I did this problem on here too. Too bad for everybody. Can you guys go ahead and try this one? Try to show this is true. As always, even just says. What does this say in complete English? Don't just read it to me. But what's it say? You can do it. You can do it. What's it say?
Limit as the function.
No. Sorry. No. I don't want to hear the word limit because I want you to kind of explain to me in English what that means.
As X approaches.
Okay, as X, be even more precise. How do you mean approach? As X gets close to 5, yes, keep going. Yes. Our outputs
Our output is 20.
should get close to 20. That's exactly what this shit says. Yes? When our inputs get close to 5, so read it with me. This is what I mean by you can read most math statements as a sentence. When our inputs get close to 5, then our outputs must get close to 20. Sometimes that works, and when it does, it's neat. Are you guys kind of with me? I need you to see how the very first thing we say is the same shit we've been saying about limits since I first talked about limits. It's just much more formally written. And we've given a symbol that means close. Epsilon is close in the y-axis. Delta is close in the x-axis. Do you guys see that? Those two mathematical statements are the two sentences we've been saying about limits this entire time. Almost like I did that on purpose. No, it's just the way you say it, but it just works out. You got to be a little careful because I do want you to be a little formal with what you're doing. How do I get this started? So we can say given epsilon greater than 0, we want to find delta greater than 0 so that when x minus 5 is less than delta, then this is true. Basically what I just set up there. It would be better if you did, but it's okay if you don't put the whole thing. So what can I do for the side work?
Go back.
Go back to where?
Factor.
Yeah, start here, yes? Start where I want to end, which is why it should feel like cheating to you. We're going to start where we want to be. So we're going to factor this thing. So that becomes 2x plus 10 minus 20 is 2x minus 10, which what can I do then? Divide by 2, because 2 is positive, so I can actually take the absolute value 2 is 2 and divide by 2. And I do uncover what I need to see. If you don't see this, you're doing something wrong. Why is this good? Because that's exactly what I will need to show up. So now I know exactly how close I need to be to 5 to make this as close as I want to be to 20. Yes?
Technically, without even doing any work, you would always know that it's going to be like, for this one, for example, x minus 5, and it's going to be epsilon over 2, because the...
Yes. Sorry. Yes. That's what I meant by some of you guys will notice. And again, I'll say this again. If this was a 7, it'd be epsilon over 7. If this was an 8, it'd be epsilon over 8. If this was a 3.2, it'd be epsilon over 3.2. So, a couple of the problems are going to be a little more complicated functions. The instant I make the function any more difficult than this, the steps get exponentially weirder. So I did assign a couple of problems like that in homework just to kind of push you a little bit. And also for those of you who are like, maybe even sort of in the direction of bored, because you're like, it's just always epsilon over that dumb thing. I want to show you how that's true because we're doing the most basic type of function. The minute you get a little more complicated function, it gets much more difficult. And I'm not trying to make you feel like you shouldn't even try the homework. Try it. But you'll see the two problems I'm talking about when you do the homework. They lead to weirder situations. And there are examples in the book that kind of show you how to step through it. Yeah.
Out of curiosity, what would happen if the 2x was negative? Like if the coefficient.
Then you would still divide by 2 because I could take a negative 2. Very quick side work. Very quick. So if I add this, yes, I can take a negative 2 out. Yes. What's the absolute value of negative 2? 2. What's the absolute value of x plus 5? I don't know. And then I divide by 2. So the reason I could just directly divide by 2 is it's already positive.
Okay.
Yes? So I kind of skip that middle step of taking the absolute value because they know the absolute value is going to be 2. Okay. Now, what do I do? Given epsilon greater than 0, let delta equal epsilon over 2. Then when x minus 5 is less than epsilon over 2, I just start doing everything in reverse. You guys can't do this, but you just rewrite all this, and you end up here, and then you're done. Yes? Just in the interest of space. Now some of you guys, I came around, you wrote quite a bit less than I did, and I was still cool with it. I'm fine, but you have to show me the important parts. If you don't write any words on this problem, you are wrong. Do you understand what I'm saying? Somebody really get me? You have to write words for a proof. Okay. How do you guys feel about this compared to when I first started talking about it? Is it better? On one level, it's better because it's just silly. It almost always works the same way for most of the functions we look at. But I did challenge some of you guys in that homework. We'll see. Sorry, buddy. Go ahead. Yeah. Okay. So he's trying to take a picture. All right. Do you guys want to go a little bit further and take a break later, or you guys? Okay, let's do that. Let's go just a little bit. I can never tell. I'm going to go a little bit further, and then we'll take a break. All right. So get in there and try out section 2.4. Here, I'll talk about one idea, and then we'll take a break. Do you guys remember? This is, by the way, this is section 2.6. So we just did 2.4. 2.4 is the epsilon-delta stuff. 2.5 was continuity. We did that yesterday. You can maybe see why I wanted to leave 2.4 for kind of like its own little thing. 2.6 is funny to me because it just says, hey, do you remember anything from pre-calculus? Do you guys remember the shortcut? Well, actually, somebody help me out. What is a horizontal asymptote? What is that? Be very careful. Vertical asymptotes are walls that say, you cannot go here. Yes? I was thinking about Gandalf. I have the shirt. I gotta be careful when I wear it though, because it's Gandalf standing on the x-axis, and the function that says, you shall not pass. And then some students took that personally. I'm like, no, sorry. It's just a joke about Gandalf. All right. So a vertical asymptote comes with a domain. I cannot use that number, so I build a wall there. So my function doesn't go there and freak out. Horizontal asymptotes. Am I allowed to intersect horizontal asymptotes? Yes. All day long. I can intersect an infinite number of frickin' times. You guys okay? Vertical asymptotes are, do not go here. Horizontal asymptotes are,
Hey man, hey, can you eventually get close to me? Come on.
so you can go through the damn thing. So here's what I mean. Here's a standard horizontal asymptote that students think of. And I put a little bonus vertical asymptote action there too. Yes? Yes? That's the standard thing that students think of. Here's another possible horizontal asymptote situation. Ya la 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 la. How many times does that function go through the horizontal asymptote? Why is it still a horizontal asymptote? Is the function get? Oh, you ready for this? This is our first reason why I love that we did 2.4. At some point, does the function get arbitrarily close to that line?
Yeah.
Yes. You guys with me? If I had just a normal sign doing this shit, the midline is the x-axis, Does it have an asymptote? Does it ever get closer and closer to the x-axis, a normal sine function? Does it ever get closer and closer to the x-axis? No, it does not. No, it doesn't. What's happening out there? Here. Here it is. Here's sine, yes? Far, close, far, close, far, close. Does it ever get closer and closer and closer over time? No. It hits it and then it goes away from it. And then hits it and then it goes away from it. It never has a point where it's as close as I want it to be forever. That's the trick. This one, is there a point where I am epsilon away? And you're all like, God damn it, Jeff. I thought we were done with that for now. No. Where did I put all my other... Dadgummit. They're gone. I had them. I had some other pens. I'll be all right. Oh, there they are. All right. I appreciate you. You're like, can I help this crazy man out? This is kind of dumb because obviously there's a point where it's further away from that, right? Right here, it's closer than those forever, yes? But then I can get even closer and say, is there a point where it's always closer than this? Is there a position, maybe starting there, is it forever, starting here, is it forever within those two lines?
No. Oh, yeah.
Yes. Do you guys see what I'm saying? So there is some number n after which the function is forever epsilon away from this line. That's what a horizontal asymptote is. Now, what is x doing to get closer to this line? What do I have to let x do? Get really... No, x. What's x doing? Whee! Getting bigger. There we go. So it's going to infinity, yes? So the way to find a horizontal asymptote, technically, is we take a limit as x goes to infinity. Now here's what's really silly. Does anyone not know how to very quickly get the answer to this problem? What did I just say? The limit as x goes to infinity. Another way to say that is find the horizontal asymptote. So this is a pre-calculus question. Yes? Does anyone remember the three situations that you could be in for rational function horizontal asymptote?
The numbers of this, like...
If the degrees of the top and bottom are the same,
you just divide.
it's just 4 divided by 2. This limit would be 2.
If the top...
Does anyone want to see why that's true? Has anyone forgotten that? Or you think your pre-calc teacher didn't tell you that, which would make me really cry? Okay, watch this. You ready? Can you guys... When am I not allowed to divide by? 0. I'm not allowed to divide by 0. Does everybody agree that this problem wants me to leave 0, way the shit behind? What am I letting my inputs do? You're really big. So am I allowed to divide by x if I wanted to? Hell yeah, because is x 0? No. I'm getting really freaking big, aren't I? I'm nowhere near 0, am I? So I could divide by x. So I'm going to be stupid. I'm going to divide by x squared. I'm allowed to divide the top and bottom of a fraction by the same thing, yes? Can anyone help me out? What do I get? What's 4x squared divided by x squared? 4. What's 11 divided by x squared? Good job. What's 2x squared divided by x squared? 2. What's 3x divided by x squared? 3 over x. Good. And then 5 divided by x squared. Okay. Now, these are now stupid easy to do, yes? When x gets really big, what does this do? 11 by gigantic is going to 0, yes? You guys with me? So that's going to 0. What's this doing? Going to 0. What's this doing? Going to 0. So what's the answer?
2.
That's right, kids. 2. That's dumb. This is dumb. This is hopefully what your pre-calc teacher showed you, and then hopefully they said, hey, let's not do that shit. Let's just make a pattern out of it. If the degrees are the same, the limit at infinity is the ratio of the leading coefficients. That's it. Why? Because that will always happen, yes? If the degrees are the same. What if the degrees aren't the same?
If the top is bigger than
Yeah.
the bottom, it's just I think one, right?
Uh-oh. Which one's growing faster? The top or the bottom? Top, all day long, yes? Bottom can't keep up. So if I have something getting bigger, 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 and the bottom is not keeping up, I'm not dividing by enough, what should I go to? Infinity. So, real quick, just to make this a little more concrete, do you all agree with me that the tops in this sequence of number are getting bigger? Do you all agree with me the bottoms are also getting bigger?
Yeah.
But the ratios are getting bigger. This is 10, 50, 333 and a third, 2,500. I mean, do you see? The numbers themselves are still going to infinity, aren't they? Even though the top and bottom are getting bigger, the top is getting bigger faster. So if the top degree is higher, the limit is infinity. Or negative infinity if there was a negative sign there, yes? So watch out for your signs. And of course, the only thing we didn't talk about yet is what if the bottom's got a bigger degree? It's a different way to do it, Jeff. It's okay.
Y equals 1.
No. The bottom overwhelms the top. So it's like 1 over 10, 2 over 100, 3 over 1,000. Those fractions are getting... So in the limit, they're approaching 0. Which we already knew. You guys were so cool when I did this shit, yes? So when the bottom's got a higher degree than the top, the limit is 0. Cool. Now, in pre-calculus, you went on and talked about slants and oblique asymptotes. Don't worry about that yet. They might come up later. Right now, I just want to know the limit. Right? Okay. All right, let's take a break. Come back at 5 till. Come back at 5 till.
Is it 25?
It's got to be some kind of a number or infinity. Can't be e to the x because I'm letting x go to something. What does e to the x look like? Start with what it looks like. Can everybody draw it? You guys know what does e to the x look like? Don't do like e. No. If I graph e to the x, what's it look like? Tell me. No? That's natural what it looks like. Yeah, there it is. Swoosh, yes. I think from your perspective, that's correct, yes? So which way is letting x go to negative infinity? This way, yes? So where's it going? Because what's here? What's here? What's here? What's here? What's here? There's an asymptote here, yes? So what is it approaching as they go to negative infinity?
0, 0.
The outputs are approaching 0. That's why there's an asymptote there. That's the whole idea of asymptote. So this is 0. Of course, what's the limit as x goes to positive infinity? E to the x. Frickin' infinity. Yeah. Because it just goes crazy. Yes? So again, knowing how the graph looks will save your ass on several occasions. What about this shit? Oh boy. That was neat. Oh, okay. Yes, I see what you're doing. I'm sorry. But be careful with... So what is the difference between tangent and cotangent? In terms of graphs? Two things.
Instead of it being sine over
True. So definitionally, cotangent is cosine over sine. Graphically, there are two major things that are different.
and versus. They're flipped over y over x. Y equals X.
Sure.
Reflected over Y equals X.
That's true. So graphically, I'm not talking about the inverse. All right, guys. If you had to, like you do, because I'm telling you to right now, could you graph tangent x? Just one cycle of tangent x. Do I have it? No, just use a piece of paper, Jeff. Here, I'll do it here. What's one cycle of tangent x look like? Can anyone tell me anything about it? Okay, I got the shape. Somebody's showing me the shape, so I'll go ahead and do that. What's going on either side?
Vertical asymptotes.
Where are they? Yeah, negative pi over 2, pi over 2. Now, what about cotangent?
It should just be swapped.
Where should why are the asymptotes of pi over 2, negative pi over 2 for tangent? Because what's on the bottom of tangent? And where's cosine 0? Negative pi over 2, most fundamentally, yes. And of course, it's 0, an infinite number of places, but we're just going to do one cycle. All right, what's on the bottom of cotangent?
Sine.
Sine, when is sine 0?
On the
Y.
On the x-axis. So when am I on the x-axis? What angles? 0 and pi. So it's going to have an asymptote at 0 and an asymptote at pi. And the other big difference with cotangent is it goes this way. So when I invert this, if I'm going to invert this thing, oh, this is getting freaky, I know. Then it's going to be approaching pi. Let me see if I can do a good enough job. And 0, the vertical asymptotes become horizontal when I invert it. Invert it? Sure, Jeff. Hit the button. And then it's going to look like this, just to do a horrible job of it. So what is the limit as x goes to negative infinity of the inverse cotangent of x? As I let x go to negative infinity, what's the limit? Pi. Okay. Is everybody with me so far? So these are little examples where earlier we were doing rational functions, which are just ratios of polynomials. And those are easy. It's only one of three things based on where the degree is higher, yes? These are little side notes of functions that also have asymptotes going on. So if I have a function that's got vertical asymptotes, its inverse has horizontal asymptotes. That should kind of make sense. What was the one I was thinking about earlier? Jeff, you completely forgot. I completely forgot. It's gone. So I won't worry about it. What about this here? I don't like this. Wait a minute. There we go. Now it's even better. Now it's awesome. Okay. Screw you, Jeff. Is this technically a rational function? No. Rational functions are polynomial ratios. Yes. And the top of this is not polynomial. But can somebody tell me, let's start off nice. What's the degree of the bottom? 1. So what's the degree of the top? Note. 1. The degree of the top is 1. Do you guys see that? Square root of x squared is x to the first power. Okay. So it works the same damn way. It works the exact same damn way. Are the degrees the same on the top and the bottom? Why is this not coming to my consideration of degree? Because the degree of a piece is the highest degree I see, and the highest degree I see is 1. So that's less. So they both have the same degree. Do you guys see that? And I don't know, you might have a homework problem that looks like this. I don't know. So how do I do it when the degrees are the same? What's the answer when I go to infinity? What is it? Yeah, what are the coefficients? What are the leading coefficients? Be very careful. Here, I'll do the bottom. The top is not 2.
minus 4.
Square root of 2, there you go. Okay. Isn't the leading coefficient up top square root of 2? Of course it is. Yeah. Are you guys at all with me? Yeah. Screen each other. Okay. Here's the ultimate hand wavy way to do this. When x gets really big, how important is it that I'm subtracting 4? Yeah. 18 trillion to the trillionth power minus 4 is basically 18 trillion to the trillionth power. It's not going to change. So that goes away. How important is the x to the 1/3 versus x to the first? X to the first is way bigger. 18 trillion to the first power is way bigger than 18 trillion to the third power. To the 1/3 power, I should say. So that goes away. This becomes huge. These kind of go away. 7 don't mean shit compared to 5 times 18 trillion, yes? So then you're left with that. And what does that reduce to? To rad 2 over 5. Do you guys see that? This is square root of 2. I don't know. Square root of x squared. X, especially because it's positive. So the x divided by x goes away and you get rad 2 over 5. I mean, that's an entirely different way of getting the exact same answer. It's less mathematical, but more conceptual. Okay, maybe. Yes?
Can you do that one more time?
Sure, I'll do it. I'll even write what I'm trying to say.
Not the whole thing, just how we get rad to.
You ready? When x gets big, this doesn't mean shit. This doesn't mean shit compared to this. This doesn't mean shit compared to this. Square root of 2 is the square root of 2. The square root of x squared is x. These cancel. Same answer. That's kind of like what teachers call the hand wavy way to do it. But to be really honest, we're applying an idea that works. So to be really honest, I think that way is valid. You don't even have to do that shit though. You just have to do, it's the same degree. So it's the ratio of the coefficients. So what about this here? What you got, Jeff? I don't know, man. Let's do 4x squared. Yeah, I like it. Yeah. Okay. Ha ha ha. Ha ha. I'll calm down. Why?
9 cubed is
What's the degree at the top?
2.
Second degree. What's the degree at the bottom?
6.
Third degree. Because what's the cube root do? Cuts things in thirds. 1/3 of 9 is 3. So the top degree is 2, the bottom degree is 3. What situation am I in then?
So bottom is bigger.
Bottom's bigger, bottom overwhelms, the limit goes to
0.
Makes sense. At the bottom, if I'm dividing by bigger, I'm getting smaller. Okay. I guess so the same rule applies between rational functions, which are officially polynomials, ratio. Not like you do one now. And then it also applies for these radical functions, because you can still determine the degree. So if you can determine the degree, you can look at it that shortcut way. Now, the mistake students make is I'll do something like this. Yes? What do you got, Jeff? Now, if you look at this, what situation am I in?
The top is bigger.
Bottom's big. They're equal.
Sure. No.
They're
What's the
equal
degree
to
at
each
the
other.
bottom?
Oh,
Does anyone else notice anything even more important than what anybody said there? The limit is x goes to 0. Yes. Can I just plug a 0 in? So my point here was, don't just assume what to do based on what you see here, right? It's kind of like the same thing. You always try to plug this in first. Now, if you try to plug this in, you're like, wait a minute, that's infinity. Then you go, oh, I'm in this situation where I have to look at the degrees. If you try to plug this in, you do it. What do I get when I plug a 0 in? 0. 0 over 1, 0, yes. So be really careful. Don't just start doing shit. Take the whole thing in. Take the whole problem in. Am I going to infinity? Okay, no, I'm not, so I don't have to think about that way at all. I'm not going to infinity. Maybe it's going to be conjugate, maybe it's going to be omnipotent. Yes? Okay. Is that all right? Oh, what else is in this section, Jeff? I don't remember. Oh my God, they do this a horrific way. Look at this. Look at this. Okay, just to show you, kind of like the textbook way to do this shit. All right, can somebody just tell me the answer? The limit? Sorry? Rad 2 over 3. Let's see what they got. It's negative, right? Because, why is it negative? Why did they get negative? Let me see. Did they change the problem halfway through? No, it's not negative. I went way too far down. It's a separate problem down here. That one's there, yes? Now look at this problem. Why is this one going to be different? Let me see. Oh, now they're going to negative infinity. Now, listen. Let me write this down. Is everybody with me? Look at all the work they did. And that's dumb, because I don't need to do more than what you already did in pre-calc, which is why you took pre-calc. Yes?
Show me the problem to go to negative infinity.
Oh, on the next part, they go to negative infinity.
On that formula, they can go to negative infinity?
Sorry?
That's the...
So this first problem was going to positive infinity.
Right.
The next part, they want to go to negative infinity. So I'm going to write that separate.
Oh,
Yeah.
sorry, that.
I'm going to write that here so we can look at it. This is a more interesting question. What was it again? It almost doesn't matter, Jeff. I know. Let me see. Sure. All right, now, here's where we got to be a little more careful. So I'm letting x go to negative infinity. What's true about the bottom that entire time? If I'm riding the train going to negative infinity, all my x inputs are negative, yes? What's true about the bottom? What kind of number will the bottom be? You could do it. What kind of number will the bottom be if I'm plugging in giant negative values for x?
Really negative.
It's going to be negative. You with me? What's the top going to be by definition?
Positive.
Radical answers can only be positive, correct? Square root answers, I should say. Yes? Cube roots can be negative. Even roots can be negative. Leave me alone. So, this is still going to be rad 2 over 3, but what did we just say? Every step of the way, the number I'm looking at is negative. It's positive divided by negative, yes? So that's why it's going to be negative rad 2 over 3.
So writing that out, could you like make the x later divided by negative?
You could sort of, yeah, right here. It's funny you said that because I was just thinking about, like, if you told yourself 3 times big negative, yes? So that'll be rad 2 over negative 3 in the limit. I don't know if that's sort of like what you're thinking about doing. Your inputs are negative, therefore the 3 would end up being negative in the limit. Maybe. The lesson there, kids, is if you're going to negative infinity, slow your roll. Yes. Just step back for a second and go, what kind of numbers am I getting out? Then the great thing is, you still look at the dumb thing as rad 2 over 3. That's still going to be part of the answer. It's just now you're going to say, is it going to be negative or positive? What would be different if the problem had been this instead? Get out of here. Negative infinity. Square root of 2x squared plus 1 over, 2x to the 4th, there we go, over 3x squared minus 5. When you plug in really big negative numbers, the top sign is positive, of course. Are you guys, because 2 reasons. I mean, 4th power of anything is positive, and the whole thing's positive. What's the sign of the bottom going to be? Positive. So what's this answer going to be? What's the degrees?
They're equal to.
Equal. So then what's my answer? Positive rad 2 over 3. Good. So I mean, again, I know the answer is going to be rad 2 over 3. I just have to stop and slow down and go, is it going to be positive that? Or is it going to be negative that? Okay. Maybe. Okay. Yes?
When it's approaching positive infinity, it's always going to be positive, right?
Well, no.
Well, if the...
Yeah, if the number itself is
Yeah.
positive, then it's more direct.
Yeah.
Because if I had a silly question like this here, right? Then it's going to be rad 2 over negative 3, yes? So when it's going to infinity, it's much more direct. You could just look at it and see. When it's going to negative infinity, you got to slow down and think about it for a second. You with me? See if the negative still stays alive, or if the negative gets killed, like the problem above this one. Here, I just killed the negative. The problem before, I didn't kill the negative, so that's why the answer was negative when I went to negative infinity. Okay, maybe. Yeah. Oh, here. Oh, this is so cool. Oh my gosh. Which one's this one? I'll do this one, yeah. Yeah. This specific one is a little bit boring, but we'll be all right. Now, how is this different from what we were just talking about? This is not a ratio, right? Yeah. What do you get when you try to plug? Listen, I want to really make this clear. Dear God. So let me do this real quick. Let me just do this while I'm thinking about it. Dear, whatever your favorite deity is, if you ever do this hurt me right now. This physically hurt me to write. You cannot. If you write this, the next time I see you, I want you to bring infinity to me. And have you ever, I keep talking about Pulp Fiction, but when they opened the briefcase, I think that was infinity in there. Maybe that's one thing it could have been. Oh. If you've never seen Pulp Fiction, you're fine, but you really should. You guys understand what I'm saying? I had a student that just would not stop doing this, and I finally just said, put BFN for big frickin' number. They just wanted to put something in there, so I just put BFN for big frickin' number, then 3 divided by big is small. Great. You just can't plug infinity in because infinity is not a thing. It's a process. Infinity is not a number. It's a process. You can't plug a process into a function. You can't do that shit. Maybe. Okay. So, coming back to this. If I do try to let x get big, what form does this take? What does this go to if I let x get big? Don't overthink it. Just let x get big. What is this approach? It just goes forever up, yes? That goes to infinity. Minus infinity. Now, if you put it in parentheses, you're fine. Because you're showing, you put it in parentheses off to the side. You're showing me that's the form it's trying to take. That's fine. I'm not plugging infinity in. I'm just writing what form it's trying to take. Believe it or not. Well, does anyone know what that is? Yes, beautiful. It's an indeterminate form. It's not 0. So let me ask you this really weird question. Does infinity equal infinity? No. If this one is going to infinity faster than this one, the answer is infinity. If this one's going to infinity faster than this one, the answer is negative infinity. If they're going to infinity at about the same rate, it could be 0 or it could be some finite number. Are you guys all with me? It's all about how quickly they're going to where they're trying to go. So this is an indeterminate form. Shit. What does it mean when I have an indeterminate form?
It could be any of them.
That means that's the beginning of my work, yes? I'm at the beginning. So what can I do? Let me help you out a little bit. I'm going to put this over 1. Can anyone see something I could do? Yes. Jeff, you could do it. One of my students had a really good idea. They're like, they should have put a back wall on radical symbol. I'm like, you're right. Somebody sort it with me? We've done this kind of thing before. We just have to remind ourselves that everything that we think is not a fraction actually is, because it's over 1. And then it's a ratio, and I can do like we've done before. What do I get up top?
X squared plus 1.
I get x squared plus 1 minus, is that cool? X squared plus 1, middle terms cancel, minus
X squared.
x squared. over this business. And now what is this? If you let x get really big, sorry, if you let x get really big, so there's this, yes? FOIL. Is that why you guys were quiet a second ago?
Yeah.
Just let me know. Yes?
It's probably better if we just leave that one.
That would be great, Ronnie. See, Ronnie's a smart guy. Much better than me. I don't pay attention. So then these x squares go away. If I let x go to infinity, what do I get now?
Big number on the bottom.
So then I get 0. Will the answer always be 0? No, it definitely won't always be 0. That's why we have to do these steps. It just, in this case, this one's kind of dumb, and I think some of you guys might have heard me say that when I first started writing this down. I'm like, this is too easy. Do you guys see this is basically x? When x gets really big, 1 doesn't mean shit. Square root of x squared is x for positive x's, yes? X minus x is 0. So I knew ahead of time the dumb answer is going to be 0. But it depends on what else is in here. The answer doesn't have to be 0. It's just that these happen to be growing at the same rate, which is why they kind of cancel each other out. Maybe. Okay. I think there's one more thing. No, not that. That one we did already. Ooh, that's a neat one. What do you guys think about this one? Oh yeah, and then I want to do that one, that's right. By the way, you guys see what that says? It doesn't say 1 over e to the x. It says e to the 1 over x, yes? Okay. There is something I could do for myself. And what else did I put in there that we haven't seen in a little bit?
The negative.
The negative 1, 0. So that means I'm approaching 0 from the left. Yes? Okay. If I'm approaching 0 from the left, every number I'm putting in is what kind of number? Negative. Which means as I approach 0 from the left, what is 1 over x approaching? Let me see if you guys are really with me. If I just look at 1 over x, what's the limit as x goes to 0 from the left of this? Negative infinity, yes? So what did I just apply? I just applied a limit law. I took this question and I brought it into the function. So therefore, what is this equal to? E to the negative infinity, which I never want you to write. So this is in this form, yes? So here's the right way to do this. Let me see if you guys are cool with this. Do you all agree with me that the power, whatever's up here, I'm going to put a T here. Whatever that is, as x goes to 0 from the left, what is that power doing again? Going to negative infinity, yes? So what is t doing? You just told me. These questions are equivalent. This makes the power go to negative infinity. This makes the power go to negative infinity. So what would this limit be? We did this one already. 0. That's neat. That's a bit more flexibility than you might have otherwise seen. You are allowed to rewrite more complicated parts of a limit by analyzing them by themselves first. You don't have to do this too often. Later it will become something we make a little more formalized. We'll see. Oh yeah, this one. Are you guys doing okay? I just want to throw several things at you so you're kind of going to feel how some of these things work. Here's a really silly one. Is it infinity? Could it be? What sign contained between the outputs? Negative 1 and 1. But is this limit going to be 0? No. Because is there any time when it stays infinitely close to 0? Or is it always going equally far away from 0 forever? Okay, so the answer is not infinity. The answer is not a finite number. Does not exist. Kick ass. Now, what's really neat is what kind of not existing is this thing doing? This is called oscillatory divergence, which is way too technical of a term, but I just want to tell you. That makes sense, because what does a sine and cosine function do? It oscillates. So if I have a function that just oscillates forever, it's never settling down, the limit can't exist. But if you just said it does not exist, you're fine. If you say oscillatory divergence, I'll have a little tear come out for you. Which doesn't make a bonus point, sorry. It's just this little tear for you. Okay. All right, good. Blah, 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 blah. Blah, blah, blah. Yes, beautiful. Already said that, already said that, and already said that. Cool. All right. So a lot of section 2.6 is built on pre-calculus concepts. Now, most of you guys, now real quick, I want to say this before I forget. Could you please fill out the survey if you haven't done it already? Last time I looked, about 14 people had filled it out. Yes, could you just do it for me, please? You don't have to answer every question. It'd be great if you would, but you don't have to. Just put some stuff in there. The people that I've looked at, what's really neat for me is most of you guys have taken math recently. Very often over the summer, like last summer I think, I had a bunch of people that said, oh, I took math 3, 4, 5 semesters ago. I'm like, oh shit. Summer calculus, oh boy. But most of you guys have taken your last math course relatively recently, which is good. I completely forgot my point with that, but that I just wanted to let you know, I guess. Okay. I had a point I was going to make, but I'm getting old. I don't know anything. So, what I want to do for the rest of the time is we're going to try to look at, we're going to come back to something that I brought up way earlier that we haven't really touched since I brought it up. Do you guys remember the secant lines we did and the whole idea of how we're going to utilize limits to do something? So what calculus does, here's the big thing calculus does, and I've already said this. Calculus looks at algebra and says, that's cute. You can find the slope of a line. Who cares? Because it's always the same thing. Yes? What's much more exciting is, what's the slope of this thing?
Wait.
Huh? Wave is a good way to say a word, but what is the slope of this thing? In fact, my question doesn't even make sense. Why is my question, what is the slope of this, not even make sense? Because what is the slope doing at every point? Changing at every point. So then the question becomes, what is the slope at a specific point? So in algebra, that was kind of dumb. If I just line 4x plus 3, what's the slope at this point 4? What's the slope at this point 4? You know, it's always going to be super cool. But now, we have a slope that is eternally changing as I move along it, yes? Okay. So let me do this. I think I want to do that first, because we'll come back to this a few different times. If I do have this, weehaw! All right, I'm going to do something you've never done before, but it's kind of silly. I've never shown this way, and I'm kind of excited about it. I've never thought to start with this, because we're about to get into something that students understandably have trouble with, because it's a little thing about making sure your brain is looking at things correctly. And you'll see what I mean here in a minute. I want to, on top of this graph, I want to graph the slope of this. That's what I want to do. So like, what's the slope at this point? 4. So I'm going to put a point right there. 4, yes? So everything I'm doing right now is I am plotting the value of the slope at each point. You can see how this is kind of silly to do it for a line. What's the slope here? 4. What's the slope here? 4. What's the slope there? 4. So then, of course, I just get this dumb thing. So this is, if if I graph the slope of a linear function, it will always be a horizontal line because the slope doesn't change. You guys with me so far? Okay. So what if I have a more interesting function? Yeah, we'll do that. Some guys, I don't know, gonna pretend like that's a good function. Like a good function. Now listen, I'm not gonna be as detailed because I don't need you to be super detailed. In fact, being too detailed takes away from the concept. So we're gonna do the exact same thing we just did. Except now the graph I'm going to make with my red pen should be much more complicated. Because what's true about every single point on this graph? The slope is changing. It's different at every point. Yes? Can you guys identify key locations where you know exactly what the slope is? Even though I didn't give us any scale. Yes?
On each of the peaks and troughs.
Yes. What's the slope going to be at each of these locations here? Is everybody cool with that? So like we said before, what's true about the slope here?
Very negative.
Very negative. And then it's becoming less negative, yes? I'm not going down as steeply. And then over here it's, so it has to be 0 right there. To go from negative to positive, I have to go through 0. So hopefully it makes sense. If I try to draw that kind of line that we drew before, the tangent line, it would just be kind of balancing precariously here, but it would be flat, yes? Same thing here, same thing here, yes? So for those positions, I can plot, so I am about to plot, this is where I should, it's all right, Jeff, I'll bring in the slope of f of x, which I'll just tell you right now, why not? Instead of writing this every damn time, here's what we've chosen to identify this as. F prime. When you see a little prime, that's the slope of the function. So if I saw g prime, they mean whatever g of x is, it's the slope of it. So let me see if you guys are cool with this. If that's 1, what is f prime of 1? 0. Good. Now, help me out. Back here. Here's where students really understandably lose touch with reality for a moment. What did you say about the slope back here? It's really, really big. Negative. Now, at each point, I'm going to plot the value of the slope. So where should my dot go to represent the value of the slope here? Would I put it here? What'd you just tell me? The slope is really big, negative. So my point has to have a really big negative value to represent the slope there. Yes? So the slope here is very big negative. What did this mean? What did this red line mean? Why is it flat? Slope is always 4. At this point, the slope is 4. Was the function negative here? Yes. What's the slope here, though? 4. Is the function positive here? Yes. What's the slope, though? Negative. What's the slope doing as I move in this direction? It's getting less and less negative, yes? It's getting less and less negative until I get to here. It's got to, and I forgot to put my zeros. Is everybody cool with this? This is going to have a 0 value here, 0 value here, 0 value there, yes? So I'm really big negative, and then I'm becoming less and less and less negative until I am 0. Now what's my slope doing after that point?
Getting more positive.
Getting more and more positive, yes?
Also, I have to put a point that shows it's positive.
Can you guys see? All right, let me stop for a minute. Is everybody roughly understanding what the shit's going on right now? I desperately, desperately want you to understand. Everything every point on this represents the slope of the original function. the slope here was really big negative, so where did I put my point? Way the shit down here. So if I'm trying to draw the graph that gives me the slope at every point, f prime of this thing better be really big negative, because I can see the slope is really big negative. And I better frickin' go here, because it better become 0 here. It's less and less and less negative, less and less and less negative until it hits here. Can you guys see, isn't this getting more positive? Yes, more and more positive until, and then up here, is it getting less positive? Now this is a little extra added bonus. I should be here. Damn it, I wish I had thought of this earlier. People at home. Good. People of the internets. All right, so it's really big negative. What am I doing here? Yeah, okay. Really big negative, so we plotted a point really big negative. Less and less and less negative, less and less and less negative. 0, 0. Positive, so I'm going to go up through here. Can you guys see somewhere in here where it stops getting bigger slope and it starts to get smaller slope? Like about right here. Do you guys see how there's like an up cup and a down cup, and they connect? And that point right there on my nose is a neat point. That's called the inflection point. We'll get to that later, but I just thought I'd throw that out there. So this is going to go. Do y'all agree the slope is getting bigger and bigger until about right here maybe? Bigger and bigger until about right there. And then it's still positive, yes? The slope is still positive, yes? It's just getting smaller and smaller positive until it hits 0. So wherever this line is that you're drawing, wherever it is above the x-axis, your original function better be going up. Wherever it's below the x-axis, your original function better be going down. When you first do problems like this, you have to stay on top of your brain. You have to say brain, because I always get students, they just sort of start to follow this. And I'm like, no, I didn't say trace the function. So you want to step back, take a look at what you just drew, and just make sure if my function's going down, am I down here and then negative? Because this is negative slope then. Okay. And then what happens after this? My slope becomes negative. And then again, about right here or so, there's a place where it's the most negative. And then and then it becomes less and less and less negative until it's 0 again. And then what happens forever after this?
It goes up.
Does anyone know what, I should have picked more different colors. The original function, does anyone know what the original function, the degree of the original function? How many turning points? Yeah, so it's a 4th degree. And what's the degree of this function we just drew? Third degree. Very interesting. What was the degree of this function? 1st degree. What's the degree of this function? 0th degree. Interesting. It always seems to be 1 degree less. I don't know why I'm talking like this. We are going to prove that later, but you're going to be doing in the homework a few of these graphs, and you will pretty much, if it's kind of polynomial in nature, the result's going to be 1 degree less. And we're going to prove that mathematically later this semester. Okay, so you're going to get some practice with this in a minute. I do need to step back for a second. Yes, okay. So now we've got this notation. This notation is very, very important. Can you guys remind me, did anybody, going way back, slope, which we used to call M, was the rise over run. Did anyone ever have a teacher that wrote it like this?
Yeah.
Does anyone remember what that symbol? They may never see it like this. You're like, you put a triangle. What? So that's the Greek letter, the capital Greek letter delta. Remember delta was the one about the distance of the x-axis? That's the lowercase delta. This is the uppercase delta. If that just means change in. If I said slope was the change in the y's divided by the change in the x's, you would agree. Yes, rise or run. Yes. So that's another way to say it. This symbol means a big step. When we do derivatives, when we do slopes in calculus, I don't know if you guys remember, do you remember the whole thing about flat earth? I had a curve and then I zoomed in so much it became a line.
Yeah.
When does every function that's continuous, when does it become a line if I zoom in a lot? Yes? So if my movements are very small, then it looks linear. Yes? If I don't go too far on the earth, I can approximate my motion with a straight line. But if I go far enough, I got to approximate it with a curve. Yes? So, this is a giant step for man. No. This, if I just go to D's instead of deltas, just take it to our alphabet, this means an infinitesimal step. I don't write the word infinitesimal very much. I'm not sure if that's spelled right. Oh well. I hear the little ding. I'm out. So delta y delta x would be like a step of 2, a step of 1. dy would be a step of 0.80 billion zeros to the billionth power to the billionth power. It's the smallest positive step you can take. So that is like what's called an instantaneous step. Maybe. If I'm on a curve, if I move at all, doesn't my slope change now? On a curve, isn't the slope always changing? So when I want to know the slope at a point, what did we have to do? We had to make the distance I go infinitely small. Okay, let me come back to that. Let's do this. This is just another way to write derivative. In fact, since I keep saying it, in calculus, we call the slope the derivative. So if I want you to find the slope function for a given function g, I would say calculate the derivative of g of x. Derivative just means the slope function. Okay. So if I have a function g of x, its derivative is g prime of x, but that's also dg dx. Or dy dx, yes. The outputs divided by the inputs. Yes?
Can we move the camera just slightly?
Oh. So real quick, if I had a, might as well give this handout out, but I'm not quite there. If I had a function that represented the number of peppers grown given a certain amount of time. So this is the number of peppers. This is the number of days. And I take the derivative, what would that mean? So if I said P of 3, that would mean 3 days later, how many peppers do I have? Yes? What would P prime mean?
The original.
No? What did prime mean again?
A specific
Slope. Now, here's what's funny. What's the other way to write this? And if you write it like this, what are the units? The change in the number of peppers divided by the change in the. So what's the units? Number of peppers per days. So if P prime of 3 was 7, that means after 3 days, I'm getting 7 peppers per day. If I wait a day, that can change. That's what's weird about slopes of a curve. If I just wait a little bit of time, the slope changes again. Maybe. That's why in the stock market, you see a stock doing this, and then you buy, and then it goes like that, because it doesn't have to continue that slope. It can immediately change its slope. Oh, wait. Okay, I should really buy. Oh, shit. Okay. That's why it's not good to day trade, kids. Okay. All right, so let me go ahead and give you this. I don't know why I'm hesitating to give this to you. Bump, 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 bump. All right, let's take a look at this. Let's see. Do you guys see the idea behind number one? What does this mean?
The slope at x2.
The slope at at 2. The slope of the function at an input of 2. So this is asking you to put those in order. What did I say? Increasing order. Which ones of these are negative?
-7.
Yeah, at -7, the slope is definitely negative, yes? So very first level pass would be, okay, this seems to be negative. Is any other slope negative?
1.
Yeah, 1, it's negative, yes? And then these two are positive. Now you can kind of, yes? Well, actually, what's f prime of 2? Let me be careful.
0.
F prime of 3 is definitely positive. F prime of 2 looks to be 0. All right, let me stop for a minute. That's the first level pass. Now, anybody that's got the same sine slope, I want to stop and think which one's more negative than the other one. Yes? Do you start to see? So, first level thing is, can you interpret the symbol that represents the question? So, math is really just you guys catching up with all the shorthand that was decided for us by mostly old white men in the past. Yes? So then we got to go, okay, this is what they meant. They meant the slope of the function at 2, because I don't want to write that every damn time. So that much I appreciate. Between the slope at -7 and the slope at 1, which one looks to be more negative? Yeah, I would agree. At -7, it definitely seems steeper down than at 1, yes?
Yeah.
So if I'm going in increasing order, what do I put first?
7.
Yeah, f prime -7. And then I would put f prime of 1. And then I would put f prime of 2. And then f prime of
3.
the last one, yeah. Not too bad, right? So this is really just do you understand what the notation is asking you? And then can you approximate the source? Yes? Go ahead and try number 2 out on your own. And, this notation here, just always think of it as change in the outputs divided by change in the inputs. That's really all that says. When I put a D, that just means infinitesimally small steps. But it doesn't change the idea. teaching a business class. But business, they use a lot of calculus. They call it like marginal cost, marginal profit, marginal revenue. Those are all for the calculus terms. Just very often they don't even know that's what they're doing. Who's got this one here?
Would it not just be dollars over months?
Yeah, it'd be more precise. It'd be thousands of dollars per month. Yes, not month. What's the end mean?
Commercial.
Number of advertisers. Yeah, thousands of dollars. Well, if I just want to talk about, yeah, you could just say dollars per ad. That's dollars they make per advertisement that they run. So just in case anybody's business-minded, the formula they came up with for their profit already includes the fact that they have to pay for the advertising, yes? That's why it makes sense. At some point, and in fact, Part B says this, Jeff, that's why you made Part B. What would it mean if P prime is negative?
The money that they're making is, they're losing money.
Well, not really. Derivatives are always about what's about to happen. So this one, yeah.
Spending more money on ads than
Okay. Yeah, they will be. If they ran one more ad, they would lose profit. Because P prime means what's happening to the function as it moves forward. So if I move one step forward, which is what's acting like the x-axis here? What's the units on the x-axis?
And so ads, number of ads.
Number of ads. So if I take one step forward on the x, this would predict I'm going to go down in profit. You guys with me? I could be at the sweet spot. What's the sweet spot? What's the sweet spot? It would be the most profit I can make. It would be the top of the mountain, yes? And this way, if P prime is negative, that could mean if you run one more ad, you go down the other way, you're starting to lose money. But that's why I'm trying to be careful. At the moment, I don't have enough information to know if they are currently making or losing money. They could be breaking even, or they could be making some money. If they went one more step, they would lose money. Okay, so however you want to write all that. Now, just to make it much more concrete, what does this mean? How many ads are they currently running?
10.
Currently running 10 ads. And its P prime of 10 is 20. So what does that mean?
10 ads will predict $28,000 made.
If they ran one more ad, they would make how much more money?
20,000.
Now, they could actually end up making not 20,000 because if they do, okay, this is where things get tricky. Is everybody semi-cool with that answer? Well, one reason you could be not cool with that answer is that's not really English, Jeff. I don't know what language that is. If they ran one more ad, and in fact, I love how I spelled ad. I will give myself a break for that because I'm a math guy after all. If they ran one more advertisement, they would predict that they should make $20,000 more. Now, what did I say? The minute you move, what changes? The minute you move, what changes on your function? The slope changes. So this prediction is only good for that immediate place. The minute they run one more ad, maybe they don't make exactly $20,000 more. I would feel pretty decently confident I should make more money, but I might make more, like 4,000 more, or I might make 30,000 more, because I don't know what it looks like if I do take that one step over. I don't know if you guys are really with me. Business, a friend of mine, he used to be a financial analyst for Dell Computers, and then he was for some other companies. And his job was to figure out what the price point should be given the way things looked. And it was eternally a guess. Because what happens the minute you change your price? Well, there's all these other variables that change outside of your hand. From one day to the next, demand changes. Other companies are changing the price. All these other variables. Are you with me? So you can make predictions with calculus. The minute you do something, calculus is like, I don't know, you just step somewhere else. I don't know what's going on there. Are you guys at all with me? So on one level, I don't blame you if you're like, well, what the good shit is this? And it's like, absolutely absent any information, it's better to know that. That's good information. I should feel pretty confident that I should run one more ad, maybe. And then I can reevaluate. Yes? Yes?
The only thing that's confusing me is if they're running 10 ads a month, do you mean one more ad as in one more unit of 10 ads a month?
Yeah, like the next month I'll run 11. And then I'll kind of reevaluate. Or they could go for broke and run 5 more and
So
just.
where did the one come from?
Okay. This means $20,000 per one ad. Because it is 20 over 1, correct? You guys with me? That is 20 over 1. You with me? What's 20? 20 over 1. Yes? If P prime had been 5/3, that would be 5,000 per 3 ads. There we go. Since it was a whole number, it's per 1 ad. You guys with me? Now, if I ran 3 more ads, does that mean I'm going to make $60,000 more dollars? No, because 3 is quite a step, and I could be in totally different. 3 could be oversaturating, and I'm like watching, like, there's that damn commercial again. I'm not going to buy that shit. You guys know what I mean? And that is also a variable that they take into account in their calculations. If you run too many ads, people are going to, like, it's going to be like a protest. I will not buy your shit. It looks good, but it's in too many ads. Screw you. Has anybody ever had that experience? No? No? Alright. I know it's less ads now with streaming, but you still get ads if you don't pay for it. You know, anyway, we're in the same place. Suppose the company currently I basically just said what we should do. Damn it, Jeff. Should the company run more or fewer commercials? We should run more, yes. If it was negative, should we run more or less commercials?
Less.
We should try to run less and then reevaluate, yes? Maybe. Because we don't know if we're at the peak. If we're at the peak and I run less, then I'm making less money, and then I can take that into consideration. It's more data. Okay. I like it. That's what would kill me if I was a business financial analyst. I don't know what function I live on. I'm just eternally getting little bits of information about parts of it, and every moment the function's changing. I would go insane. More insane. Okay. Blah, blah, blah. We already talked about it. Okay. Number 3, I think we already did a problem like this. Go ahead and consider this question. What would it mean for values near x if f prime of 3 was negative 1?
So it's gonna be like a rise over everything?
Yeah, totally.
So it would be, x would be 3, and then it would be negative 1 for 1.
It's going down.
Yeah, one way to answer this question, okay, does anyone have an answer to that question? Let me just start there before I tell you. Yes?
The slope of the tangent line at that point would be -1.
Good. So the tangent line at that point would have a slope in that. I could also say I would predict if I took 1 step forward, I should expect to go down 1. But again, the minute I take 1 step forward, not 3, because the 3 is just where I am. If I take 1 step forward, it's negative 1 over 1. This predicts I would go down 1. Why might I not go down 1? Because the minute I move at all, I'm in a different slope situation. Maybe. So there's a few different ways to answer this. If we also know this, can we find the equation of the tangent line? And we've done this before, yes? What does this tell me?
The slope doesn't.
M. And then do I know x1, y1? Not yet. Well, yes I do, don't I? Do I? Yes, all right, here, Jeff. Here. I circled it for myself. Go ahead and make that tangent line equation. Go for it. Just to make sure you guys are with me. What's M? Negative 1. What's the point we're working with?
3, 5.
3, 5. And then I can use this equation.
Is B?
Huh?
8.
I don't know. We're gonna find out. Yeah, if you go 3 back, you go back up to 8, yeah. So you can figure it out, pretty straightforward. I just try to force this equation, like I said, it comes in handy later. So this is not even pre-calc, this is freaking algebra. Y minus what? 5, because that's the y piece, equals the slope times x minus the x piece. So you get y equals negative x plus 3 plus 5. Hi-ya. So I don't have a clue what this function is. But given that behavior, I know what a tangent line to it would be. We don't know what this function is. I didn't tell you what the function could look as weird as it wants to. But I know right at 3,5 it's got a tangent line. Well, I guess, is that right for you guys? Yes, that's right for you guys. Yes, that's right for you. Yes? Okay. Maybe. Maybe. We are often going to use this notation, but I desperately need to keep this notation alive because it becomes much more important as you progress in your calculus. Okay. All right, so last thing for today. Ooh, yeah. Can you guys do these two for me? This is exactly like the two we did earlier with the line, and we drew the graph, the slope, and then the W, and we drew the slope. So I want you to draw the slope for those two graphs. Exciting. This is exactly the same as this stuff. Yes, it's exactly the same as this stuff. Yeah, totally. Yeah. Just right here, you put open circles. Because the slope right at that kink in there is undefined. It's just to really make sure. What's the first point you should plot when you have this kind of problem? The zeros. Those are nice anchor points. In that case, if you're drawing and you're not coming anywhere near what you plotted, you're like, I'm doing something wrong. I gotta go through that damn point. It's just a nice visual anchor. Always feel free to work with people near you if you want to. Bounce ideas off of them. That's like the very first example we did. So absolute value is weird. It's got two linear functions. So their slopes are going to be just constant lines. What changes on this side? The slope becomes positive. So on this side it'll be at positive. So like, I really want, so like, what's the slope at this point? Negative 1. So you put negative. What's the slope at this point? Negative 1. So that's why it ends up just being a straight line. For every point, it's got a slope of negative 1 because it's linear. The slope doesn't change. On the other side, every point's going to have a slope of. What's the slope here? What's the slope? Anywhere on the line. This ring. One. So the slope here is 1. The slope here is 1. Yeah. There you go. So if I have a linear function, the slope, your function should be flat because the slope isn't changing. It's constant. Yeah. That's it. Now just connect those. One, the other one's going back, and the other one's going. So this one's going forward. This one's going back. Yes, because that's where those. Yes. Yeah, we'll talk about it, but these should be over. Because right at that point, the derivative, the slope is not defined. Yeah, right at that kink. I was just about to ask that. Yeah. Exactly. I couldn't zoom in and make it linear at all at that point. So technically, this discontinuous. Yeah. The derivative is discontinuous. All right, let's take a look here. By the way, what degree is this? 3rd degree. So I already expect I should get a 2nd degree answer. What's the 2nd degree look like? Parabola. So what's true about the slope here? Big pi. In fact, let me just do my own advice. It's flat about right here, and it's flat about right here. Yes? Okay, so it's really big positive, but it's getting less and less and less positive. Then it becomes negative, and about right here somewhere, it's the most negative, and then it starts becoming less and less and less negative, and then it becomes positive and getting bigger positive. All right, so that's a janky little parabola, but it's close enough. Not poor parabola. Isn't that kind of cool? You can guess what the answer is going to look like based on your degree of the original function. So you can kind of check afterwards. Absolute values suck in general. Did I say that last time? They're like hidden piecewise functions. They're like a horrible choice we made. We made a lot of bad choices in history, but a lot of us math people, we were high a lot of the time. What is the slope here?
-1.
And where is it -1?
From 5
All the way. So it's -1 all the way. What's the slope? Don't worry, we'll talk about something specific in a second. What's the slope here?
1.
And it's 1 forever. Now right here, and I love the way somebody put this. If I zoom in forever, I'm not going to zoom in forever. If I zoom in forever, does that ever become flat? That point? No, it's always going to be a little mountain. Yes, inverted. Yes? Forever. So the derivative, the slope at that point is undefined. What I like to say is, this is a plane that I don't want to be on. Thanks for choosing Spirit Airlines. We're going to be cruising up. God, we're all dead. We're dead. We can't survive this quick of a turn. So the slope instantaneously changes. So right at that kink, it's undefined. Would you say, is the original function continuous? The original absolute value? Total. Is the derivative function continuous? So the technical name for that, where is it discontinuous? Where is the derivative function discontinuous? At 0. So this would be not differentiable at 0. The absolute value of x is not differentiable at 0. So what does it mean for it to be differential at a point? The derivative function has to be continuous at that point. If the derivative has a discontinuity, then it's not differentiable at that point. I'm just getting us ready for that question coming up. Yes? So this happens to be not differentiable at x equals 0. So with that in mind, can you guys tell me, where is this function not differentiable?
X equals 3.
X equals 3, okay. Where else?
X equals negative 2. No.
Yeah, x equals negative 2. So wherever there's a kink, yes?
Yeah.
I was going to say don't shame the function, but it's okay. Wherever there's a kink, so negative 2, and where else?
Negative and 0.
No?
Oh, I mean 1.
1. So at negative 2, there's a kink in it that the slope instantaneously changes, so it's not differentiable right there. It's not differentiable right there for the same reason. It's not differentiable here because the function itself is not even continuous. But also the slope instantaneously changes there too. All right, let me stop for a minute. Is everybody with me? What about part B? Where is it not differentiable but it's still continuous?
Negative 2.
Yeah, negative 2, it's not differentiable, but it is still continuous.
And 1.
And at 1, it's not differentiable, but it is still continuous. So I just want to put that there just to show you how there is a connection between differentiability and continuity, but they don't mean the same thing. Yes? There's a connection, but they don't mean the same thing. Yeah, sure. We'll do this one last thing and then we'll head out. This is where things get exceptionally trippy. Okay, you guys thought this was trippy, yes? Maybe? No? If you didn't, that's neat. Enjoy that. Once this clicks, it becomes much easier and you just have to really stay on yourself as you're doing this. This is the reverse. Do you guys see what I'm saying? This is the graph of the slope already. And look how I say this. Sketch a possible function. Now real quick, if I said to everybody, in fact, let's do this. Can you guys make an XY plane real quick? Just a really simple XY plane. Yes? No, I'm sorry. I'm really sorry. On your paper. I really appreciate everybody. I'm sorry. I lost a little capital there, but we were ready to play along, man. I don't know what I was going to make you do if I didn't. No, your nose is a point on it. All right, on your XY plane, can you graph a line with a slope of 1? Roughly, right? Doesn't have to be perfect. So, could somebody have done this and it would be right?
Yeah.
Could somebody have done this and it would be right? Could somebody have done this and it would be right? Could somebody have done this and it would be right? Could somebody have done this and it would be right? Do you see how many lines can I draw that has a slope of 4? I'm sorry, of 1. How many lines can I draw that has a slope of 1? Infinite number of lines. So when I give you information about G prime, that is not enough information to get the function. I just know the slope. So help me out. This is very trippy, so let's do this together. Can you tell me what's true about G? What's true about G given this information right here? What's true about G in this region? Slope must be
Positive.
3. Be very specific. So from -5 to -2, the slope of my function must be 3. Where is the function though? It doesn't matter. So I'm going to give myself room. I'm not going to put it up here because then I'm going to run out of room as I try to do slope of 3. Yes? So I'm going to start way the shit down here. I really want you guys with me. Are you with me? You're like, I don't know, Jeff. So I can start here and I go up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1. Does it have a slope of 3 through that whole region?
Yeah.
Yes. So, given this problem, I could expect as many different answers as there are students in the room. Do you guys see that? What I'm saying right now is actually bigger than you think. If I just give you slope information, I know how the function's moving, I don't know where it is. What's true in the next little region?
It's 0.
Slope is 0. So to be really honest, if you wanted to, this could be your answer. But all you need is a flat line anywhere. So the slope is 0. So wherever you want to put it, I'm going to put mine. I got to be a little careful. Do you see how I made that filled in? So I better make this open here. So I'm going to have a flat line here. Is everybody with me? Yes.
Can you make it where they're connected or that?
Oh, I could totally do that, yeah. In fact, one semester I did that. I could make this connected, sure. In fact, it's so funny you say that because I was considering saying sketch a possible function where g is continuous. So if I wanted to make g continuous, I could just do this. Wherever I left off, I could pick back up, yes? I don't know what I want to do there. It doesn't matter. You can put that anywhere. You guys get that idea? What's true in the next section?
It's -2.
So now if I wanted to make this continuous, I can start here and go down 2 over 1, down 2 over 1. And now what's true about the slope here?
0.
Careful.
I mean, it's 1. So.
It's 1. So now I can just go up 1 over 1. Did I have to make it connected? No. Each segment I could put in an entirely different place. Maybe you guys are with me. Maybe. And then what about this guy? What's true about the slope here?
It's negative.
No. This is G prime, yes? This is G prime. What does G prime mean? This is G prime, yes? What does G prime mean?
It's the slope.
Slope. So what is the slope at -5? It's 1. See it?
Oh.
It's 1. So I better draw something that's kind of going up there. But then what's the slope at -3?
0.
Okay. So it's going up with a slope of 1, and then it becomes flat here. Yes? And then what's the slope after -3? Negative until here. And then what happens to the slope? Yeah, what's the slope here? No, be careful. This is G prime, yes? All the outputs are the slope. So what's the slope starting at -1? What's the slope? -1. So now I'm going to go down 1 over 1, down 1 over 1, down 1 over 1. I just happened to randomly make up there. What's happening to the slope now? Here it's 0, yes?
Yeah.
I don't need it there, Jeff. It's just gotta, but here it's negative and then it bottoms out. Slope is 0 here. And what happens to the slope after 3? No. No. What's the slope at 3? 0. What's the slope at 4? 1. What's the slope at 5? 2. So now it's got to be going up faster. Yes? If the slope is flat, that means if the slope function graph is flat, that means the original function has got a constant slope. If the slope function is diagonal, that means the original function is curved. Okay. That was a major push. That last one is really, really, really tricky. So that's enough. I'll see you guys tomorrow. What's happening tomorrow? Quiz.